Okay, so we're gonna look at reducing radicals or simplifying radicals today. Uh, so, and then we're also gonna talk about finding square roots of negative numbers, which is something I've kind of mentioned in passing in a couple times. I think if you look back to like one of the first things we did with quadratics when we were looking at vertex form, and we had you guys finding the x and y intercepts. Uh, one of those problems that we ran into in the notes and in homework, there was end up being a square root of negative, and I told you all can't square root negatives. That means there's no x-intercepts. And then just the other day, we were talking about what zeros were. I talked to you guys about zeros and solutions and roots and x-intercepts. And we said, what does a graph with 2 zeros look like? And we drew that. What does a graph with 1 0 look like? What does a graph with no zeros look like? And this is as we hit what we're about to do tomorrow and Monday, we're going to start seeing like how do we get these equations that have no zeros or no solutions or no x-intercepts? Like where is that coming from? That really does deal with square rooting negatives. So how do you square root a negative, and which I imagine will be new to all of you guys. I'm not sure if you guys have reduced radicals before or not. I can't remember what happens in Algebra 1. It's been so long since I taught it. So I'm sure it's changed a little bit since I taught it too. So this might all be new to you, or you might have done a little bit of this reducing radicals or simplifying radicals business. So a couple quick things. What is a radical? Okay, this symbol right here is a radical. Just this symbol. Okay, so that's called a radical. This number here is called a radicand. That's the radicand. So when we have a radical like this, it symbolizes a square root. Okay, what's implied there is that word square. There's a little number that we can put on a radical, which is called an index. The implied number is that there's a 2 there, okay, because it's a square root. There, we could also have a cube root, right, or a 4th root, or a 5th root, or a 6th root, or a 12th root. It doesn't matter, okay? So we can go from 2 up. If it's anything but 2, you need to put what it is there, okay? But today we're just going to be focusing on square roots. There's no such thing as a 1th root. There's no such thing as a 0th root. Okay? Those don't exist. And the lowest thing we have is a square root, right? What number times itself twice is something else. Okay? That number, again, is called the index. So whatever number you see out there would be the index. It'll tell you what root you're taking. If there's nothing there, then it's a square root. That's the implied root. Okay? So a couple little things there. So ways to say this, you could say square root of 27. You could also say radical 27 is another way to say that. Okay. What I'm going to show you guys here first is a couple different methods of simplifying or reducing a radical. Basically saying what's something that the square root of 27 is equal to. Right? Since the square root of 27 isn't a nice perfect number, it's not like the square root of 25. How do we simplify that down? How do we find out what it's equal to? Okay. So the first method is called the product property method. It basically says that if you can look at that number, that radicand, and you can break it into its factors, you can break it into its factors. I can look at a number and break it apart and say that, well, I can just rewrite this as the product of 2 other radicals, 2 other square roots. Okay? But what's really nice is if one of those could be a perfect square, it's really what we want to do. So if we look at the square root of 18 and say, hey, can I break apart 18 in a special way, not just in any old way, but so that one of the things I break it into is a perfect square. So like breaking it into 3 and 6 wouldn't be very helpful because neither 3 or 6 is a perfect square. But breaking into 9 and 2 is helpful because 9 is a perfect square. Okay? And so once I break that 18 apart, then I can reduce whatever parts I can reduce. So since the square root of 9 is 3, I can reduce that or simplify that. But we don't know what the square root of 2 is, so it just stays put. So the square root of 18 simplified or reduced is 3 times the square root of 2. Okay? So ever hear the way I say that? 3 times the square root of 2, or 3 square roots of 2 is generally how I say it. Or you could say 3 radical 2. Okay? Different ways you could say that. Right? 3 square roots of 2, 3 times the square root of 2, 3 radical 2. Okay? How we could say that out loud. Okay? If I wanted to type that in the chat, right, you guys are going to be answering some questions for me later. So we could just type 3 square root 2 like this, okay? I didn't know this until third hour. Somebody showed me this. So 3, and then you hit Option V, and it brings up the radical symbol. So 3 option V, and then you can actually type in the radical. Okay, so as you guys are answering stuff back to me later, there's 2 ways you could do that. Okay. So the product property method is not really the method I like much. This is the method I learned when I was in your shoes, but I prefer this new method I'll show you guys here in a second. Okay, what the product property method requires is that you guys look at a number like 27 and be able to break it into factors, ideally where one of those factors is a perfect square. Now 27 is not too bad because you look at 27 and it's 9 times 3. It's like, okay, what's the square root of 9 times the square root of 3? Okay. And then you're like, oh, well, square root of 9, that's just 3. And then the square root of 3 we can't do anything with, so it's just 3 radical 3. But when the numbers start getting weirder, bigger, it gets harder to do that, right? When there's lots of sets of factors, right? 27 only has one set of factors besides 27 and 1. It's 9 and 3, so it gets pretty easy there. But you look at 98, there's multiple ways to break 98 up. So how do you know which way to do it, okay? That's where I think this other method I'm going to show you guys is better, okay? So that's the product property method. Again, you have to be able to find perfect squares within a number, pull them apart, and then you can reduce it from there. But you guys won't see me do that anymore. All right, I'm going to show you what's called the sock method. I learned this quite a few years ago, and ever since then, this is the way I've taught it. I think it's so much better, okay, for where you guys are at. If you're really into numbers, the product property method is better. It's faster, but this is usually better for people kind of like where you guys generally are, Algebra 2 students generally are. Okay. So you do need a calculator for this though, because we're going to be doing lots of dividing. Okay. So the sock method is basically a factor tree, but it's an organized factor tree. So I'm not just going to be spreading branches all over the place. Okay. Sock method depends on you guys taking the smallest number out that you can. So what's the smallest number that goes into 98? Okay. Prime number, by the way. What's the smallest prime number that goes into 98? Which would be 2, right? It's even, has to be divisible by 2. Okay. And then so 98 divided by 2 is what? All right, Kyle? And we want to keep doing that same thing until we're down to primes. Okay. Is 49 prime? No. All right, but 49 is not divisible by 2. Sometimes when you look at a number like 49, like, oh, 49 is 7 times 7, right? Those are prime numbers. 5 doesn't go into 49, 33 doesn't go to 49. Okay? And 7s are primes, right? So we are down to our prime factors there. And so why this is called the sock method is because the numbers we want, the numbers we need, are here in this little sock off to the side. Okay? The 98 and the 49 were broken apart. They're gone. Okay? We're purely looking at the 2s, the 2 and the 7s. Okay? So there's our little sock. Okay? What we do after we get it all broken down to primes is we go looking for pairs. Remember, this is a square root. Okay, so in order for something to come out of this, it has to be a perfect square. All right, what's a perfect square? Well, 7 times 7 is a perfect square, right? Because 7 times 7 is 49, and we know the square root of 49 is 7. So the analogy I like to use here, guys, is like this. So your little 7 over here, okay, your little left 7, and your little buddy right 7 comes over. Hey, can little left 7 come out to play? And then your mom's like, oh yeah, since there's the 2 of you, you guys can go outside. Right? So if you got a buddy, you get to go outside. Okay. But if you're lonely, you have to stay inside. Right? Why am I using these words inside and outside? Because we have outside of the radical, and then we have inside of the radical. So the lonely guys stay inside. So if you have a buddy, one group of 7s comes out, right? 2 7s gives me one group, so 1 7 gets to come out, okay? Because that's a 49, we're square rooting it, comes 7, okay? Not 49, not 14, okay? And then anything that's lonely stays in. So the square root of 98 is equal to 7 times the square root of 2, or 7 square roots of 2, or 7 radical 2. There's different ways of saying that. That is the reduced or simplified version of that radical, okay? So we break it apart in an organized way. We look for pairs. Pairs get to come outside. Lonely guys stay inside. Okay? If this had been a 3, if we'd been trying to cube root, which is something that we'll do later in the year, we would have to find groups of 3. If it had been a 4, we'd have to find groups of 4. And if it had been a 5, we'd have to find groups of 5 in order for them to come out. So that index tells you how big the group has to be in order to go outside. Okay? But this is a square root, so we just need 2. I'm going to do that again over here. So negative square root of 45. Now, this is not what I was talking about earlier with how do you square root a negative. Now, this is not the square root of a negative. This is a negative square root. Okay? This does not equal this. Okay? They are not the same thing. Okay? This is purely what's the square root of 45 with a negative on it. That's it. Okay? So we'll get to the negative square roots. All right, this is a negative. That's not what I meant to do. Again. This is a negative square root. This is a square root of a negative. Okay? So they are different. We'll get to this later. Okay? So negative square root of 45, essentially what I want to do is just break apart 45. 45 is not even, so I can't get 2 into it, but does 3 go into 45? I always want to start with the smallest thing I can. Does 3 go into 45? Yep, right, got that 15 times. Okay. It's 15 prime. Nope. So we need to break apart 15. What's the smallest number that goes into 15? Yeah, right, Jared, 3. That's 3 times 5, right? And then 3, 3, and 5 are all primes, right? So there's our little sock. Oops. Okay. Again, these numbers here are broken. You can cross them out if you want to. I usually don't, but okay. So with that negative, all I have to worry about is just putting that negative out there. That's all it's doing. Okay. Then I go looking for pairs. I have a pair of 3s. Look for my lonely guys, ones that aren't grouped. I got a lonely 5. If you got a buddy, you got to go outside. If you're lonely, you stay inside. So negative square root of 45 is equal to negative 3 times the square root of 5. Okay. And I would type that negative 3, option V, 5. Okay. Or I could type negative 3, square root 5, like that. So these problems are pretty easy because they're small, right? Those are pretty small socks. So let's look at a bigger number, see how it kind of works out with something like the square root of 600. Okay, how do we reduce or simplify that? Okay. Process does not change though. We always start with the smallest number we can and take out of it. And that's an even number, so I'm going to take out a 2. So 2 times 300, still even. So 2 times 150, still even, which is 2 times 75. So 2 doesn't go into that. Does 3 go into 75? Yep, 25 times, right, Kyla? So 3 times 25, and then 25, of course, is 5 times 5. Once we have it all broken apart, what do we do? Buddy up. Okay, Audrey. Like that, buddy up. So we got buddies here. And we got some buddies here. All right, so we got 2 sets of buddies. All right, and then we got some guys that weren't buddied up. All right. So if you got a buddy, you got to go outside. So 2 comes out. 5 also comes out. If you don't got a buddy, you're staying inside. So there's a 2 inside. There's also a 3 inside. Well, if you think about all this math we were doing here, right, it was all division. If I'm going back the other way, I'd be using multiplication. Okay, so this is all multiplication. So of course that equals 10 radical 6. 10 radical 6, 10 times the square root of 6, 10 square roots of 6. Okay, different ways of saying that. The multiplication is implied there, right? That I don't put a dot there, but it's implied. This is 10 times the square root of 6. want you guys to do this. Find that for me. Type your answer in the chat. Mr. Wildman, I'm assuming you're joking.
Oh, I'm sorry. What did you say, Mr. Baker?
I said, I'm going to assume you're joking.
Oh, I mean, I didn't hear you said. I just heard you say, "What's that?" And you circled 120.
Yep. I want you to do it, not type in your calculator.
That makes sense. I don't know. It's just second nature at that point. Just type it in my calculator. Sorry.
Something's missing, Tian. Something's missing, Jake. Audrey. Wait, no. That's not right, Audrey. You're close, Audrey. There you go, Jake. Outside's messed up, Audrey. Camilla, what you getting? June, what are you getting? Sophia, what are you getting? Mason Hare, what you getting? Good, June. Here you go, Sam. Two squares of 30. What's wrong, Audrey? You had the 30, right? You had 4 squared to 30?
Yeah, I got the 4 because I thought we were supposed to multiply the outside.
So remember, each group gives us 1. Right? 1 group of 2s comes out. 1 group of 5 comes out. Right? 1 group of 3s comes out. Remember, this is equal to 4. As we square root the 4, it brings us a 2. This is equal to 25. Obviously, we square root it, it gives us a 5. Right? So that's
yeah.
1 group gives us 1 on the outside.
All right.
So Sam, you were talking about like you didn't think it was right. Okay. So how do you know if it's right? Okay. So remember what this was. This was a 4. Square root of 4, right? It gave us 2. What's 4 times 130? Or sorry, 4 times 30, Sam? Right? So 4 times 30 would get us back to 120. So you can at least see if it's equal. It doesn't necessarily mean that you're right, because if you forgot to like group something up, but at least you can see that they're equal. Does that make sense, Sam? 4 times 30 is 120. Okay. Or if I look over here, 10 squared is 100. So 100 times 6, 600. Okay, does that make sense? 100 times 6, 600. Okay, so you can check to see if it's equal. Again, not necessarily right, because if if I group the 2's here, but I didn't group the 5's, and so I'd have 2 times 3 times 5, which would be 150. So 2 squared is 4. 4 times 150 is 600. So this is equal to that, but it's not fully simplified. So it's like if you take a GCF out, or what you think is the GCF, right? But you didn't take everything out, and you check it by redistributing to see if you got back to the original expression. You would get the original expression back, but you didn't actually take the full GCF out. So, but you can at least see that they're equal to each other. You didn't just completely screw it up. So, all right, so let's look at something a little more complex. I'll do this with you guys. So what we have here is a radical expression times another radical expression. So this says -5 square root of 3, or square root of 6 times 3 square root of 10. So this is a times, right? Not an x. So what happens here, essentially, it's almost like terms, okay? The normal pieces get to multiply each other, and the radical pieces get to multiply each other. Okay? So if I want to go to do this to start off with, the first thing I do is say that this is equal to, oops, dang it. It's equal to, so -5 times 3 would be -15, and then square root 6 times 12 is 72. Okay? So first thing we do is just multiply them. And normal parts times normal parts, radical parts times radical parts. And then I go look at that 72 and say, well, I need to break apart that 72. So 72 is even, 2 times 36. 36 is even. So that's 2 times 18. 18 is even, which is 2 times 9. 9, of course, is 3 times 3. Okay. You guys good here? So Jarrett, what do I do now? Now we've got it all broken apart. What do we do next, Jarrett?
This part's where that's why I get confused on this next part.
Okay.
I know how to break it down, the 72,
Okay.
but to get to the 15, I don't necessarily.
No, don't worry about the 15. I'm just asking about what do we do with this?
Oh, you group.
Group, right? So I want to find pairs, right? So we got a pair of 2's, and we got a pair of 3's, right? And what happens with those pairs, Jarrett? I got a pair of 2's. So what's that mean?
The inside one goes inside of the.
Okay, so that lonely 2.
Yep.
Look at that lonely 2, so he's stuck inside. What about that group of 2's and that group of 3?
I think they go on the outside.
On the outside, you got a buddy, so you got to go outside. So 2 comes out, 3 comes out. All right. 15 is just going to come on down. All right. Yeah, remember what this said. All right, how do we read that, right? It's -5 times the radical square root of 6, right? It's 3 times the square root of 12. It's -15 times the square root of 72. All this is just multiplication. Right? Even right there in between, we don't generally write that one there between them, but it's still multiplication. It's all just multiplying together. So 15 times 2 is 30, times 3 is 90. So I'd have -90 square roots of 2. -90 square root of 2. So a really common mistake is for people to just like have that 15 just kind of flit off, right? So, but it just needs to fall down and then get multiplied by whatever else comes out. Okay? Does that make sense, Jared?
Yep.
All right, I want you guys to try D here. Shoot me your answers back in the chat. Good, Sam. Cam, what are you getting? Kaylin, what are you getting? Good, Kyla. Caitlin, what are you getting? Brian, what are you getting? Good, Jake. Zoe, what you getting? Mason, what are you getting? Oh, you did. Good job, Zoe. Job, Caitlin. Lost something, June. At the outside, right? You dropped something, Tian. Really common mistake. I think you did the same thing, Audrey. Make sure you don't bring out 4s. Just bring out 2s. Remember, every group just gives you one of those numbers. June, it looks like you dropped this 7 to me. Tian, you didn't bring your 6 down. Jared, I'm not sure. Yeah, it is. I'm not sure what happened with you.
I know what I did.
June, Tion, do you see what you got? Did you drop that 7 off? Okay. Yeah, you're good, Andre. All right, cool. Okay, so that's multiplying radical expressions. Okay, nothing too crazy going on there. Just be careful. All right, so here's kind of big new thing for today. Okay, the imaginary unit. Okay. So, if you think back, it's kind of weird to think about this, like hundreds of years ago, as people were mathematicians were working on working with all these equations and stuff like that, trying to look at quadratic equations and figure out what they could figure out about them. We talked about some of the applications of quadratics too, and how they're around us, with motion and studying the orbits of the planets and stuff like that. It's all based around quadratics. So it's something that people are really interested in. They kept running across equations like something like this: x squared plus 36 equals 0, right? And then they would go to try to solve it, and so they move the 36 over and then say, well, x squared equals negative 36, and then you square root to get rid of the square, and you end up with x equals the square root of negative 36. But there is no square root of negative 36. There's no number times itself that's negative 36. And so they just kept running across over and over again problems like this, where they'd end up with these answers that they couldn't find. And there was this importance to them for these mathematicians to be able to have answers to these. And so basically what they had to do was say that, well, since there's no real answers to this, right, we have to create our own number to do this. And so the number that they created was I. And so when we write an I, we always put a little bit of a scriptiness to it, okay? Because we do not want it to look like a 1, right? So I always write mine, it kind of looks like a little J, okay, a backwards J. Even if you put a little dot over, that could get lost really easily, okay? So there's always a little bit of a curve to an I when you see it written out, okay? So something handwriting-wise you need to make sure you're dealing with. Okay, so that's the imaginary unit. And what I is equal to is the square root of negative 1. And this is essentially vocabulary for you guys, okay? And in order for you to be able to rest with what we're doing, you need to know your vocabulary. Okay? So as we go to do what we're doing tomorrow, what we're going to do Monday, if you don't understand how to square root negatives, you got a problem, okay? And so this is how we're going to square root negatives, by using I. Okay? So you need to know this. It's like going to biology class and not knowing what a cell is, and then they're like, blah, 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 this cell, blah, 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 that cell, muscle cells, brain cells, you're right. Yeah. So this is vocabulary. Okay? You need to know that. This is what
Mr.
Yeah.
Is there a way you could write the upside down J on the keyboard?
Not really. If you have different fonts and stuff, usually the Times New Roman italicized I is actually really good for this, but not with what we got. With what we're doing right now, when I type I, you guys can see that it's an I, right? It's not a 1. So it's pretty obvious typing. I just want to talk about handwriting. We really got to be careful. Okay? But yeah, usually if I was going to type something out for you guys, I would use this Times New Roman italicized I. It's pretty good looking. So, so how do we use this, right? How do we take something like the square root of negative A, okay? Or what we were just talking about, the square root of negative 36, and figure out what that's equal to, okay? And so what we use is something we talked about earlier, the product property of radicals, that I can take that number that's negative 36 and I can pull it apart, right, into its factors. Well, what multiplies to be negative 36? Well, most obviously 36 and negative 1. So instead of looking at the square root of negative 36, I can just think about what's the square root of 36 and then what's the square root of negative 1 and kind of separate them. Well, thankfully, we know the square root of 36, right? That's 6. And then we just defined what the square root of negative 1 was, is I. And so that's just 6 times I. Well, just like how we say 6 times x is just 6x, right? 6 times I is just 6I. So we kind of treat it like a variable, even though it's not a variable because it's only one number. It's just I is only the square root of negative 1. We talk about it because it's a letter, like we talk about variables. So this is just 6I. I could throw a different one at you, something like square root of negative 100. Okay. It's the same thing as the square root of 100 times the square root of negative 1. Square root of 100 is just 10. Square root of negative 1 is just I. So the square root of negative 100 is 10I. Yeah, again, just like, I think that was that you, Jake, that was asking about that? Yeah. Just 10I, that's all you would write.
Okay, thank you.
Yeah. Oh, what I am definitely not asking you guys to do, okay? I am not asking you guys to use the sock method on things you should know, okay? I didn't sock out the square root of 36 to find it was 6. I knew it was 6. Okay? I didn't sock out the square root of 100 to find out that it was 10. I knew that it was 10. You guys should know those, okay? We're using the sock method to find square roots that we don't know, right? You didn't know what the square root of 120 was. So we found a way to figure it out, like to simplify it, okay? So just be aware of that, right? If you know the answer, then just give me the answer, okay? The sock method is there for the ones we don't know, all right? Does that make sense? Okay, so that means I want you guys to tell me these two, and you should be able to tell me them very quickly. Simplify both of those. Send those to me in the chat. And if it's taking you a long time, you're thinking too hard. Good, Jarrett. Good, Jake. Nope, not Audrey. Good, Eddie. Good, Tian. Good, June. What's the other one, June? Cam, what are you getting? Camilla, what are you getting? Zoe, what about you? Aiden. There you go, Audrey. Good, Zoe. June. Caitlin, what do you got? Brian, what do you got? Mason. Yeah, just use an I, Sam, not a J. But yes. Yeah, the J part is for handwriting issues, just so we can differentiate between a 1 and an I visually easily. When you're typing it, just use an I. All right, cool. Okay, so 3I and 8I, okay? So when it's just a square root of negative, right? It's not a negative square root. We did that earlier, right? So negative square root of 9 equals negative 3, right? Square root of negative 9 equals 3I, right? There's a difference, okay? So pay attention to that, right? So if you know the answer, it's easy to do, right? When we don't know it, right, this is why we have the sock method, okay? Shouldn't be stuck on the negatives. The negatives are easy, right? Anytime we see a negative, Aiden, what is it? Inside, when we have the negative inside, what's the answer always going to have in it? That's it, yeah. Okay? Don't make it harder than it is. That negative inside is just an I. Boom. And then you just deal with the numbers. The numbers are more difficult than the negative. Okay? When I look at this, I know this is going to be an I. This is what I don't know. Okay? This isn't the work. This is the work. Okay? So I look at the square root of negative 126. First step is to break it apart. So square root of 126 times the square root of -1. Yeah, I'm going to go ahead and sock out the 126. So 2 times, what's that, 63. 2 does not go into 63, but 3 does, 21 times. 3 goes into 21 7 times. Yeah. So socking out the 126. Okay. Got a pair of 3s. Lonely 2, lonely 7. Okay. 3 comes outside. So we got a 2 times a 7 inside. And then this is just an I, right? But it's just multiplying. So that multiplication is going to follow me down here. Okay, this is just multiplying also, right? So what we might be tempted to write is this. Okay, might be tempted to write that, but we are not going to write that. And the issue again here is purely handwriting. Okay, mathematically that's fine. Okay, the issue here is handwriting. If I get what I like to call a leaky radical, it kind of drifts over there, and you kind of get this question like, is the I under the radical or is it not under the radical? I can't tell. Okay, so we do not want to leave that ambiguity where it's like, I don't know where the I is. Okay, so what we do to fight that, okay, we always write our problems like this. All right, come here, you. Our I is going to go there. So 3I, option B, 14. Okay. Or 3I square root 14. Okay. So, think about we have a convention set up, right? If I say what's x times 3, right? X times 3, we write 3x. Okay. So in the same way, if I said, hey, what's x times the square root of 2, right? Well, we might think that we should write square root of 2x. Again, if that radical gets leaky at all, like starts to eke over that x at all, it gets really unclear, right? Is the x supposed to be under the radical or not? Is it the square root of 2x? Or is it the square root of 2, times x? Which one is it? Because those are different. So to fight that, we don't write it that way. And it's not good handwriting. We always write x radical 2. So our general convention is to put letters after numbers unless that number is a radical, and then it goes in front of it. Okay? Purely to keep that confusion out of it. And you will never see me write something like that after the radical so that it stays clear. Okay? So that's what I expect from you guys too. 3I radical 14, not 3 radical 14i. Okay? So I want you guys to do this one. Good, Sam. Good, Audrey. Good, Jake. Good, good job. The square root, if you can type out the word, SQRT if you want, Aiden, or it's option V. Good, Kyla. Good, Jarrett. Not quite, Aiden. The pair gets to go outside. The lonely guy stays inside. Definitely not Zoe. Don't use your calculator like that. Sock it out. Yeah, I'm definitely not looking for decimals here, guys. We need to be looking for reducing or simplifying our radicals. Yeah, I always make sure, I'm always circling and then underlining Aiden. So I really make sure I'm separating everything. Those threes go together on the outside. That one's the only one by itself. So. All right, one last thing I want to show you guys real quick. It's not going to be anything crazy new. It's just looking at a problem with multiplication and the negative in it. So that's really no big deal. So again, at multiplication of two radicals, we look at the outside numbers, the normal numbers. So in this case, I have a 2 here, and then I'd have a 1 right there. All right, so there's just a 1 there. And then I have my inside numbers. Oops. So the 18 and the 6 need to multiply. So getting this, so 2 times 1, of course, would just be 2. And I have my radical. 18 times 6 is, what, 108? So this would be negative 108. Okay. And then from there, it's just what we've been doing, right? So I'm going to sock out the 108. Or I guess I should rewrite it first. 2 times square root of 108 times the square root of negative 1. So break it apart. Take the negative out, okay? And then I'm going to sock out the 108. So that's 2 times 54, which is 2 times 27, which is 3 times 9, which is 3 times 3. Go looking for buddies, as Audrey likes to say. So I don't want to lose track of that 2. That 2 comes down. This 2 also comes down. This 3 comes down. And my radical. And this 3 stays in. And then my I pops there. Again, that's all just multiplication. Good job, Jake. So equals 12I radical 3. Oh, you had radical 6. Jake should be 3. Oh, that looks good. So doing that with the imaginary numbers, really no different than what we did earlier, okay? As far as multiplying, just don't forget your I. The negative on the inside, that's an I. Negative on the outside, it's just a negative. Okay? You guys have a worksheet in your Google class. There's a back and the front, so just watch out for that, but it should be pretty straightforward. Just reducing your radicals, simplifying radicals, no. Only thing you should be using your calculator for is the division. Okay, as you're doing your trees, you shouldn't be typing that in your calculator and trying to get an answer out of it. Okay. I do want to see your work on this. Okay. But you need this skill in order to do what we're going to do tomorrow and what we're going to